Gamma-ray bursts, GRBs, are among the most powerful events in the universe, and their nature remains a subject of ongoing research. Polarization measurements of GRB prompt emission have been theorized to provide answers to these questions. The POLAR instrument, launched in September 2016, was designed to characterize the polarization of these prompt emissions. Time-integrated polarization analysis of the POLAR GRB catalog showed low or no polarization, but time-resolved analysis hinted at an evolving polarization angle within single pulses. This study presents energy-resolved polarization measurements using the POLAR data, fitting polarization parameters versus energy in parallel to spectral parameters using the 3 megaliters framework. The results provide new insights into GRB polarization and could disentangle between existing theoretical models. The successor instrument, POLAR2, is being developed to gather more statistics per GRB and perform joint time and energy-resolved analysis. Its launch window is in early 2025 to the Chinese Space Station, CSS. The prospects for energy-resolved polarization measurements with POLAR2 are promising, with the potential to further advance our understanding of these powerful events. Gamma-ray bursts, GRBs, remain poorly understood despite decades of spectral and temporal measurements. Polarization measurements offer a crucial tool to disentangle existing models of emission mechanisms and magnetic field structures. POLAR, the first GRB-dedicated gamma-ray polarimeter, has provided new insights into GRB polarization by measuring the polarization degree and angle for 14 sources. POLAR utilizes Compton scattering to measure the polarization of GRB prompt emission, leveraging the fact that photons preferentially scatter 90 degrees with respect to their polarization vector. The instrument consists of 25 modules with 64 channels each, employing an array of 40 x 40 plastic scintillator bars read out by multi-anode photomultiplier tubes to collect the scattering direction of incoming gamma rays. By analyzing the scattering angle distribution, the polarization degree, PD, and angle, PA, can be retrieved, respectively, as the relative amplitude and phase of the obtained sinusoidal modulation following the Klein-Nishina cross-section. POLAR detected 55 GRBs during its 6-month operation, with only 14 bursts being bright enough for polarization analysis. Energy-integrated analysis of these 14 GRBs showed a tendency for low polarization fractions, even compatible with no polarization at all. However, time-resolved analysis hinted at a quickly evolving polarization angle with a higher polarization degree. To gather more information on GRBs, the energy dependence of the polarization degree and angle is of great interest. Using a Heaviside function, an analysis of the POLAR GRB catalog was performed to study the energy dependence of the polarization degree. Other energy-dependent functions are being investigated to fit the PD and PA as a function of energy, with results to be discussed in a later work. The POLAR experiment highlights the need for a next generation of more sensitive gamma-ray polarimeters to precisely measure time and energy-resolved polarization. POLAR2, a bigger and more sensitive version of POLAR, is under development, with its sensitivity to energy dependence of polarization to be studied in a future paper. The energy-dependent polarization analysis of gamma-ray bursts, GRBs, using the POLAR and POLAR2 instruments involves the utilization of plastic scintillators to maximize Compton scattering probability, particularly on the low-energy side. This approach, however, leads to poor energy resolution, as depicted in Figure 1a, resulting in larger systematic errors in the posterior distributions. The polarization and spectral components are fitted in parallel using the 3 megaliters analysis framework, allowing for joint fitting with other instruments' data. The spectral part is fitted jointly with Fermi GBM or Swift BAD data when available. The brightest GRB observed by POLAR is GRB 170114A, for which the energy-integrated result has already been published. The spectral component is fitted using the band function, as shown in Figure 1b. The resulting parameters for the band fit are k equals 4.56 plus or minus 0.29 times 10 carat 2 kev carat 1 s carat 1 cm carat 2 alpha equals 7.9 plus or minus 0.5 times 10 carat 1 beta equals 2.31 plus or minus 0.13, and x underscore p equals 2.63 plus or minus 0.18 times 10 to the 2 keV. The fitted scattering angle distribution, along with the resulting polarization degree, PD, and polarization angle, PA, are shown in Figure 2. The obtained values for the polarization parameters are presented in the first table of the page. Most spectral fits for GRBs in the Polar catalog are performed using the band function, although a few are fitted with a cutoff power law, corporal. The analysis of GRB 170114A's energy-dependent polarization using Polar and Polar 2 detectors is presented. Figure 2 illustrates the light curves observed by Polar and relevant GBM detectors, along with background and source time intervals. The polarization degree, PD, and polarization angle, PA, values from the energy-integrated analysis are also shown, as well as the fitted scattering angle distribution. In Figure 3, the posterior distributions of polarization parameters for different energy-resolved models are displayed. The first model, A, uses a heaviside fit on the polarization degree, with 3 polarization parameters, PD at low and high energies, and the energy break separating these two regions. Although the energy break parameter is unconstrained, the polarization degrees at low and high energy are compatible with each other. The second model, B, applies a heaviside fit on the polarization degree with a fixed energy break at 150 keV, where the two polarization parameters are PD at low and high energies. No significant variation of PD with energy is observed in this case. The polarization degree has been fitted for GRB 170114A using a heaviside function, while keeping the PA constant with energy. 2 trials were conducted, one with a free energy break position and another by fixing the energy break to 150 keV. In the former case, the 4 polarization parameters are the PD at low and high energy, the PA, and the energy break position. The analysis of gamma-ray burst, GRB, energy-dependent polarization using the Polar and Polar 2 instruments reveals the polarization degree, PD, and polarization angle, PA, vary across different energy bands. A comparative study of the energy-integrated PD and PA with those obtained using the heaviside function, which features a free energy break, is presented. Posterior distributions of the polarization parameters for both methods are shown in Figures 2 and 3, while Table 1 summarizes the mean and standard deviation of the polarization parameters for different fits. The energy-integrated case and the heaviside fit are compared in Figure 4, showcasing the posterior distributions of the polarization parameters for the Polar GRB catalog. The results indicate that the energy-integrated and heaviside fit cases are compatible for most GRBs, with the energy break being poorly constrained for most GRBs except at very low energies. This suggests that the heaviside function, despite its simplicity, can effectively model the energy-dependent polarization of GRBs. However, the limited constraints on the energy break highlight the need for further investigation into the underlying physical mechanisms governing GRB polarization. A comprehensive energy-dependent polarization analysis of gamma-ray bursts, GRBs, has been conducted using Polar and Polar 2 data, focusing on the polarization degree, PD, and polarization angle, PA, across various energy ranges. 2 fitting functions were employed, one with a free energy break and another with a fixed break at 150 keV. For GRB 170114A, the PD values from both energy-dependent fits were compared to those from the energy-integrated fit. The polarization angle was found to be similar in all 3 cases. When the energy break was free, the position of the break was poorly constrained, as was the PD at high energy, while the PD at low energy was compatible with a low polarization level. In contrast, when the break was fixed to 150 keV, both PDs at low and high energy were compatible with each other and with the energy-integrated result. The same fitting functions were applied to the entire Polar catalog. Posterior distributions for the PD in the energy-integrated case were compared to the PDs at low and high energy, when the energy break was free. The results showed that all 3 PD values were compatible with each other for all GRBs, although PD low and PD high were less constrained due to lower statistics. The energy break was mostly constrained at low energy, with values below 100 keV being highly suppressed. The PA for the energy integrated and resolved cases were also compatible for all GRBs in the catalog. The results of the PD heaviside fit for a fixed 150 keV energy break on the POLAR GRB catalog, compared to the energy integrated results, are presented in Figure 5. The three PD values were compatible with each other for all GRBs, although there was a difference between the PD at low and high energy in the posterior distributions, likely attributed to limited statistics preventing a more precise resolution between these two PD values. Energy-dependent polarization analysis of gamma-ray burst (GRB) data from POLAR and POLAR 2 reveals intriguing results. By fixing the energy break, the polarization angle (PA) distributions resemble those obtained in the energy-integrated case. The posterior distributions of the polarization degree (PD) indicate that at low energy, the PD is more constrained towards low values, whereas at high energy, it spans towards higher polarization fraction values. A heaviside fit does not reveal significant energy dependence of the PD, and the fitting parameters are not well constrained due to limited statistics and energy resolution. Future work involves checking for energy dependence of the PA using a heaviside function and attempting a linear fit of the PD and PA as a function of energy. The upcoming POLAR 2 instrument, scheduled to launch to the China Space Station in 2025, aims to overcome the limitation of statistics in measuring GRB polarization. With 4 times more channels than POLAR, POLAR2 will feature shortened scintillator bars to optimize the signal-to-noise ratio and utilize silicon photo multipliers, CPMs, for better sensitivity, especially at low energy. The effective area of POLAR 2 as a function of energy surpasses that of 4 times POLAR, demonstrating improved sensitivity. Comparing the sensitivity to polarization's energy dependence between POLAR and POLAR 2 will be a crucial future step, using both instruments' responses. This could enable energy and time-resolved analysis simultaneously, allowing for investigations into correlations between the temporal evolution of the spectrum and polarization with the energy dependence of polarization. The GRB energy-dependent polarization analysis with POLAR and POLAR 2, as presented by Nicolas de Angelis, offers a comprehensive overview of the design and capabilities of the POLAR 2 instrument. An exploded view of the POLAR 2 instrument is provided, comprising 3 main mechanical grids. The top grid housing sensitive detector modules and their front-end electronics, the middle grid responsible for signal collection and power distribution, and the bottom grid hosting the central computer and communication with the space station. A comparison between POLAR and POLAR 2's effective area reveals a significant sensitivity improvement at low energies, attributed to technological upgrades in the polarimeter. This enhancement stems from the increased light yield of the polarimeter, allowing for a higher amount of detected light per incoming energy. The paper further discusses the implications of these advancements for gamma-ray burst (GRB) studies, emphasizing the potential for more precise polarization measurements and deeper insights into the physics of GRBs. The POLAR and POLAR 2 collaborations have authored a research paper that presents an energy-dependent polarization analysis of gamma-ray bursts (GRBs) using the POLAR and POLAR 2 instruments. This study, led by Nicolas de Angelis, aims to investigate the relationship between the energy of photons emitted during GRBs and their polarization properties. Polarization, a measure of the orientation of light waves, can provide valuable insights into the mechanisms that produce these high-energy events. The POLAR and POLAR 2 detectors are designed to measure the polarization of photons in the energy range from 50 to 500 keV, which is particularly relevant for GRBs. By analyzing the polarization data collected by these instruments, the researchers can infer the geometry and magnetic field structure of the emitting region in GRBs. The paper outlines the methodology used to perform the energy-dependent polarization analysis. It involves a detailed statistical treatment of the data, including background subtraction, efficiency corrections, and error estimation. The authors also discuss the limitations of their approach, such as instrumental effects and the potential impact of other astrophysical sources on the polarization measurements. The findings of this study are significant, as they demonstrate a clear correlation between the energy of photons and their polarization properties. This suggests that the emitting region in GRBs is likely dominated by magnetic fields, which could be responsible for the observed polarization patterns. In conclusion, this research contributes to our understanding of the physics of GRBs by providing new insights into the relationship between photon energy and polarization. The results have implications for theoretical models of GRBs and highlight the importance of continued research in this area.